Good day. So for learning task 2, we're going to answer several questions in Klein's Organic Chemistry 2nd edition. So without further ado, let's begin. Problem 8.92 states, we have seen that an E2 reaction generally proceeds from a conformation in which the beta proton is anti-beta-planar to the leaving group. A similar geometric requirement is also observed for other types of reactions such as the one below. Under acidic conditions, compound 1 rearranges to form mechanistic intermediate 2, which then undergoes 3 additional mechanistic steps along with the loss of an N2 leaving group to give product 3. The conversion of 1 to 2 is beyond the scope of our current discussion. Draw a mechanism for the final 3 steps as described. X. The alkyl group anti-beta-planar to the N2 plus group undergoes a 1-2 shift to allow a backside displacement of N2. Y. The alcohol oxygen attacks the resulting carbocation. And Z. The resulting oxonium ion is deprotonated. So this is the compound that is being talked about in the problem. So we're going to provide the mechanisms for X, Y, and Z and give product 3. So this is the overall reaction, but we're going to divide that into small steps so that it can be easy to digest. So for reaction X, this is what happens. So you have here your carbocation, which is anti-periplanar to the N2 leaving group, undergoes a 1,2 methyl shift, alkyl shift rather. So that in turn bonds with the nitrogen, which leads to the leaving of this N triple bond and creates this carbocation. That is step X. Now for Y, the alcohol here, which has an excess of electrons, it has lone pairs, would attack the carbocation, leading to that oxygen being bonded to the carbon as shown in this mechanism. And now for Z, you have the deprotonation of the alcohol. Now, I used here hydroxide, but it can be any other base. Bases are really good at deprotonating stuff. So you have here your strong base, which then attacks the H of the alcohol, and that in turn gives the electrons back to the O, which would then give us this product. Now, I just stretched a bit the geometry, the structure of this compound, but generally, when you rearrange it, this is still the same answer. So for problem 9.94, reserpine can be isolated from the extracts of the Indian snakeroot Wolfria serpentina and has been used in the effective treatment of mental disorders. R.B. Woodward employed the following reaction sequence in his classic 1958 synthesis of reserpine. After compound 1 was prepared, it was treated with molecular bromine followed by sodium methoxide to afford compound 2, which rapidly undergoes a Michael reaction to give compound 3. Now propose a plausible mechanism for the conversion of 1 to the short-lived intermediate 2. So this is the compound that they're talking about. You have there your starting compound, which is treated with molecular bromine and then sodium methoxide to give this intermediate 2, and it undergoes a Michael reaction to give us 3. But we're only going to convert or provide the mechanism that would give us this short-lived intermediate 2. This is the overall reaction that takes place, but we're going to again divide that so that it can be easy to digest. So you have here the attack of the bromine. Now, you have here your alkene and your elemental and their molecular bromine. Now, what it does is that the alkene attacks the bromine and the bromine also attacks the alkene, which leads to the bromine being bonded to both of the carbons that are part of the alkene which have the double bond. So you have here your bromine. By the way, that reaction kicks out the other bromine and gives a bromine anion. Now we have here these two carbons that are bonded to that bromine, which they took from the molecular bromine. Now, one may be inclined to think that the other bromine would also attack the other alkene, but no. The alcohol here is strongly nucleophilic. It's more nucleophilic than the bromine anion, so that would attack the carbon here, which would form a bond. Why would it attack carbon? Because it's partially positive, because the bromine is hogging all the uh, electrons to itself, because bromine is more electronegative. So there you have now the oxygen, the alcohol rather, bonded to that carbon, and then the other bromine now comes into play to deprotonate that alcohol. Now that bromine deprotonates that alcohol, which gives us this product here. Now we have two, but we are still missing the alkene here, and we still have the bromine. So what we're going to do is employ sodium methoxide, which would eliminate the bromine via an E2 reaction here. It would attack the hydrogen here, and then the bond will form here, and that will kick out the bromine, which will give us this product. This product is the short-lived intermediate 2. Now lastly, problem 12.36. Kakon is the root of an Asian plant that has traditionally been used in Chinese medicine. It smells fruity, winey, and medicinal. A study of the volatile components of kakon, those responsible for the scent, resulted in the identification of 33 compounds, including 2,5-hexanedione. Propose a synthesis of this diketone starting from 3,4-dimethylcyclobutene. So we have here 3,4-dimethylcyclobutene, and we're going to subject that to synthesis so that we can synthesize 2,5-hexanedione. So, by observation, one may use retrosynthesis to from this atom here, 2,5-hexanedione, to give us back 3,4-dimethylcyclobutene. Now 3,4-dimethylcyclobutene has an alkene, and 2,5-hexanedione has two double bonded oxygens. What mechanism can be used? What reagent can be used rather to give us two different double bonded oxygens and would break this 3,4-dimethylcyclobutene? The most plausible would be via the use of ozonolysis. But before we can use ozonolysis, we're going to shift this alkene from here to here, because if we break the bond here, we're going to have these two substituents here. So for the process, so this is the overall process. As for the mechanism, it will come soon. Okay, so we have here the mechanism. So to remove the alkene, you subject it to hydrogen bromide, which would then lead to the addition of bromine here. And then to kick out the bromine and form again the double bond, we're going to use ethoxide. I use sodium ethoxide, so that ethoxide will kick off the bromine via an E2 reaction, and then rinse and repeat, so that the double bond would go from this part to here, where the two methyl here between the two substituent methyl groups. Now, as said, after the movement of the alkene from here to here, the double bond from here to here, we're going to subject it to ozonolysis. Now, ozonolysis is very, very useful because it gives us these two double bonded oxygens. So you see here the mechanism. The alkene attacks this oxygen, and that in turn attacks that, gives that electrons here, and that bonds to here. We're going to have this cyclic uh, pentagon here. And then there's going to be a rearrangement of the electrons, which would lead to the breaking of this bond here. And you will have this structure. Then via DMS or dimethyl sulfide, it will take that oxygen and it will lead to the double bond, and it will lead to the oxygens here to form a double bond with the carbons here. Now, once we have this structure, we can rearrange that, unfold that to form this product. That is all. Thank you for listening and have a great day.